In this section, we discuss piezoelectric sensors. This is a vast topic, and it's in the short time that we have available, it is not possible to cover all aspects. So I will give some basic definitions, discuss some applications, how it operates in principle, give some examples, and some considerations of the size, electrical connections, boundary conditions, and so on. And I will try to give you some references where you can look further. So for piezoelectric sensors, we use, we can consider all four constitutive piezoelectric equations, and those parts which relate as independent variables either pressure or strain, as an independent variables charge and voltage describe functioning of sensors. Any of these can be used, and any of these relationships is used. The most common ones are those where stress is applied and either voltage or charge is measured. And you will see that there are some important practical differences whether we use, whether we measure voltage or charge. Let's first see what is the size of the direct piezoelectric effect, how much voltage or charge can we get. We are all more familiar with the voltage, so let's look at that. So we will take a relationship, this relationship here, present voltage as field as voltage over L and pressure as force over area. Rearrange terms to see what voltage looks like, and we will see that voltage depends, is proportional to the force and also dimensions of the sample. Now let's see what kind of coefficients we can get. First, we know that G is equal to D over epsilon, so we need the D coefficient, permittivity. We consider here a piezoelectric ceramic with a D coefficient of 100 picocoulomb per Newton. That's what you would get for typical hard PZT. Permittivity of about 1000. Farad, 1000 in relative units, and we consider a cube of about 1 by 1 by 1 centimeter. We get that if you put all these numbers in the formula above, you will get something like 10 volts output for 10 newtons. Now 10 newtons is equal approximately 1 kilogram. And this you can easily do with your fingers. So if you take a PZT ceramic and you press it just hard with your fingers, you may generate 10 volts, which is a lot. Now the piezoelectric coefficients in our material, practically important material, range from 1 picocoulomb per Newton to about 1000 picocoulombs per Newton. Quartz would have 2 picocoulombs, PMNPT would have 2000. So I'm talking here about orders of magnitude, and in the mid-range, about 100 picocoulombs per Newton would give you 10 volts. Note also that this depends on dimensions, so you would get larger voltages if you take samples that are longer and having a smaller area, and that has to do with the capacitance of the sample, which is then smaller because that maximizes this G coefficient. Equivalent of having a smaller permittivity. You will see later on that for a converse effect, we have units of meter per volt. So what I'm saying here is that coulomb per Newton is equal to meter per volt, and you can convince yourself transform Coulomb per Newton, and you will get meter per volt. It is very useful that when you are working with a direct effect, that you are expressing it in Coulomb per Newton, and when you are working with a converse effect with actuators, to express piezoelectric coefficient in meter per volts, although numerically the two values are exactly the same, thermodynamically equivalent, as we said before, but it's much recommended that you do that. So where is piezoelectric effect used? There are many applications. I will mention only a few. In aerodynamics, for example, pressure in wind tunnels. You know, when they are testing aerodynamicity of a car, shape of the car, they put it in this wind tunnel and blow the gas around it, and then depending on the shape of the car, you will have a different pressure on different parts of the car, and that pressure in the wind tunnels is actually measured with piezoelectric materials. In biomechanics, you can measure forces in orthopedics. So you put piezoelectric materials strategically placed at a different place in your shoe. You walk, and then each sensor will send some force, and from how those forces are distributed, the doctor can tell you whether you walk as you should, or whether you are applying a little bit more forces on the outer side or inner side, whether your spine is bended, and so on, all kind of information. Piezoelectrics are used a lot in automotive industry, in engines, to test for knocking, pressure. Then for collision forces, you know, those tests with the dummies when they crash a car on an obstacle. These dummies have pressure sensors everywhere to see what forces act on the different parts of the body. Those forces are usually measured with piezoelectric materials. In aircraft engineering, piezoelectrics are used in landing gear systems, for hydraulic systems, and so on. In processing industry, pressure during injection molding, also in food industry, in cutting forces. You have, for example, in machine industry, if you have a piece that you want to cut and you have a blade here, and that blade oscillates left and right, cutting, removing the material. Now at this position here and in this position here, the pressure on a blade may not be the same, and very often you would get that blade cut something which is not perfectly flat. But with the help of piezoelectric materials, you can control that pressure, apply a little bit more force at the ends than in the middle, and so on. So you can control your cutting better. So there is a lot of interest in piezoelectric materials from the machine industry, packaging industry. In material testing, for measurements of impact and vibration tests, part of that is done with non-dielectric testing with ultrasound, and we will talk about transducers later. And in the same category are in nautical applications, underwater sound detection. We actually use what is called transducers. Now, the word transducers, any sensor and any actuator is a transducer, because they transform mechanical energy into electrical, or electrical into mechanical. Transducers do the same, but they work at high frequencies, very often at a resonance frequency, and that's a little bit different. So we will talk about sensors, actuators, and then at the end of the course, transducers. Some transducers can be used as sensors. These are just names. What should we measure? Should we measure electric field, voltage, or should we measure charge? Well, one important difference is geometrical dependence of the effect. In with the G coefficient, where we are measuring, applying a pressure So this would be pressure. Sometimes I use letter X. When we apply pressure and we measure voltage, we notice that voltage depends on length and on area of the sample, as I just explained previously. And that puts some limitations on how you can do your experiment. When you look at a D coefficient, longitudinal, this is valid only for a longitudinal response. The force, applied force, and the resulting charge for a given force doesn't depend at all on the dimension. You can take long or you can take a flat or long sample or cubical sample. You will always get for a given force the same charge, and that simplifies things a lot. Also, with the voltage, there is another problem, and that is that voltage measurements depend on impedance of the sample. And when you maximize voltage, you are actually also having a large impedance of the sample, and that may be difficult to measure. While in charge, the charge amplifiers work in a different way, and sometimes measurements are easier. So you can consider these different things. The second important consideration is the temperature stability of the response. Actually, it's a temperature stability of the piezoelectric coefficient. And here it turns out that that G coefficient is better than D coefficient. Why? Well, let's look at temperature coefficient of G coefficient. So what is temperature dependence? You take the value of a coefficient at room temperature, and then you look at how much this coefficient changes as a function of temperature. You take the derivative with the temperature, okay? So you calculate this. That's the temperature coefficient for any property. Now, G is equal to D divided by permittivity. And when you find derivative of this, you get this. So temperature coefficient of G coefficient is temperature coefficient of D coefficient minus temperature coefficient of permittivity. As it turns out, from thermodynamics, one can, Landau-Ginzburg-Demonstraer theory, one can get that the piezoelectric coefficient is proportional to epsilon and Q, electrorestrictive coefficient. This doesn't depend much on temperature, and you get that most of the temperature dependence of a D coefficient comes from permittivity. And here you have that the temperature coefficient of G is the difference in temperature coefficients of D and epsilon. So this is almost zero, not exactly, but almost zero. And therefore, with respect to the temperature, G coefficient is much more stable than D coefficient, at least in ferroelectric materials. You can make a temperature coefficient of a D more constant if you connect a capacitor in parallel with the sample. This can be done, but that introduces another element in the circuit and is usually not desirable. So what kind of piezoelectric sensors we have? Well, the simplest one are so-called axial force sensors, in which you have a piezoelectric material. We will always speak about ferroelectrics because then we have a polarization, and so we can easily distinguish two sides, but it would work, what I'm going to say, even for those materials that are not polar in absence of electric or a mechanical field. So if you have one element, you either use Q or voltage to measure, but what you can also do, you can pile these elements in a series, mechanically in a series and electrically in parallel, and you will get that charge that is developed is proportional to the number of elements that you have. This is especially useful for quartz, which has a piezoelectric constant of only 2 picocoulombs per Newton. But if you put 2 of them, you will already have 4 and so on. One important thing that I should mention is that piezoelectric sensors are not good to measure static forces over a long time, and the reason for that piezoelectric elements themselves always have some leakage. Quartz is much better than ferroelectric materials. It has much better resistance, and also there is some leakage through the measuring instruments, cables, and so on. So if you apply scale, this is time, and then you look at the pressure, you apply pressure like that, you will find out that charge looks something like this. So I should draw this more realistic. So the moment when you apply pressure, you will measure some charge. That charge will remain constant for a while, but let's say after some minutes, half an hour or so, longer in quartz and shorter in ferroelectric materials, it will start drifting. You will start losing that charge, and you would have an impression that the force has been lost while you just have a leakage through your sample. So alternative is to use piezoresistive effect. In a piezoresistive effect, which is a 4-rank tensor and thus present in all materials, quartz is very good piezoresistive materials. You have that resistance depends on a pressure. So if you apply static pressure, resistance will be changed indefinitely. You can easily measure it with the AC signal, and mostly these static forces are measured with the piezoresistive elements. Also some accelerometers and so on work on a piezoresistive effect, but they are, let's say, complementary rather than threatening each other's for the same application, although there are some overlaps. You can use piezoelectric effect to measure acceleration. You have what is called seismic mass or proof mass. You put it on your piezoelectric element, and then if there is acceleration, that mass times acceleration will exert a force on piezoelectric material, and the stress that you get is equal to this. The voltage will be given with this formula, and this here defines the sensitivity. So it will depend on the mass. The bigger mass you put, the more sensitivity you will have. It depends on the G coefficient, and the voltage divided by acceleration will give you what is called sensitivity. So the more voltage you give for a given acceleration, the better sensitivity you have. There is another type of piezoelectric sensors, and these are so-called biomorphs. Now, let's consider single element piezoelectric. Let's say that it is polar, and then let's bend it like this. Now, on a compressive pressure, this end of polarization will give you, let's say, I don't know, positive charge, and this end on on a tension will, let's say, give you a positive charge, and this end, which is opposite, will on a tension on a compression give you exactly the same charge because you are changing. Here you have pressure which is positive, and here you have pressure which is negative, and you are also changing the direction of the arrow, or you are applying these two different pressures or two different sides of polarization vector, and therefore you will have a zero charge or current between these two planes. So bending for homogeneous bending for a single element piezoelectric material will not work. But if you put the metal there, so let's say we put here a place of the metal, and then this so-called neutral plane will be moved from the center of the piezoelectric element in such way that compressive pressure here and tensile pressure here, or vice versa, will not be exactly the same. And then you will get some net charge. This is called unimorph. And with the bimorph, you have two ways to do that. You can make a series bimorph element electrically in series, or electrically in parallel. Okay, so here you have that on this side, where you have let's say a negative, and here where you have you also have negative here. Okay, end of vector, and this one will be under tension, and this one will be under compression. So the change here and here will not be the same, and you will have a net voltage or net current, net charge in the circuit. This serial bimorph also has the advantage that if there are temperature changes, these two elements will produce pyroelectric charges which will cancel each other. So that's an added value. While in a parallel bimorph structure, it may be easier to make it, to put elements because you are piling them in the same direction. In any case, we are using here this expression to calculate the pressure. You see that we are using H31, so it's transverse piezoelectric coefficient and not longitudinal. There will be, of course, longitudinal pressure, but we are the piezoelectric coefficient, which is of interest, is this deformation along the length. It's compression not along the polarization, but perpendicular to that which matters. And for typical values, you can easily get several volts. Bimorphs are sensitive to very low forces, which is good. A big block of quartz or PZT will not deform much under low forces, but a bimorph will. However, it cannot measure large forces simply because it will break. So one has to be careful there. The same element, exactly the same construction can be used in a reverse way. If you apply voltage, it will bend, and therefore can be used as an actuator which provides large displacements but very small forces. So the displacements here can be large. You can use them to make sensors. You fix on one end of a bimorph a proof mass, seismic mass. You move it, it will bend through the inertia, will give you voltage or charge, which you can use as an accelerometer, for example, for seat belts in cars. narrowly related to piezoelectric sensor functioning is energy harvesting. If you apply mechanical force, and we are surrounded by mechanical forces everywhere around us, you will get charge. You can take that charge and store it in a battery. So you can harvest that mechanical energy and transform it into electricity. We usually by energy harvesting mean transformation of one type of energy into electrical energy. We can harvest solar energy, mechanical energy, and so on, gravitational energy, and transform it into electrical energy. And you can do this easily with the piezoelectrics. For example, you can put piezoelectric elements in shoes. You would like to use polymers for this, which are flexible. And as you walk, you will apply pressure and you can collect that charge or use voltage directly for different applications. I will not talk much about this. You can check this website in Ireland by Tyndall. And it's interesting to go a little bit historically. The first piezoelectric shoe was made by Trevor Bayliss in Britain. And if you are interested in this, you can also read this relatively old paper by Sedano and Inman on energy harvesting from piezoelectric materials. We can have a whole course on energy harvesting. I will not say more about that at this point. One thing that you should remember, piezoelectric energy harvesting cannot solve any energy problems. It's too small. What it can do, it can provide you small amounts of energy where it is immediately needed, so that you either don't have to use batteries, which you have to replace all the time, or to charge the batteries, which can remain there for at that place. So the piezoelectric, if you have one typical application that people are dreaming of, would be to have a pipe in which you have a vapor, for example, in a power plant, and this pipe is vibrating because there is lot of thermal energy there, and you need to check periodically whether there are any cracks in that pipe. So you need to monitor structural health of this pipe. What do? You put piezoelectric elements there, and with ultrasound waves, you can see whether there are changes in a material, whether there are developments of the cracks. Ultrasonic material can be a high temperature piezoelectric, but you have to drive it with something, and you have to send that signal to some control center. And for that, you may need wires. And wires are very inconvenient. You may need kilometers and kilometers of wires. Even in a car, you use a very large number of wires from battery to the end part of the car, which brings, I think, several dozens of kilograms of weight to a car. So even though you have a battery, you wouldn't like to use it at the back of your car. And there is a lot of mechanical energy there. So what you do, you put some piezoelectric elements in addition to these ultrasound elements, which under vibrations of the pipe collect that mechanical energy. You provide it either directly or through batteries. So this is a piezoelectric energy harvesters. You provide ultrasound device. It sends a signal. You collect a signal back, and then the same element that is doing energy harvesting or another element can send it wirelessly to the control center. And for wireless sending, you also need energies. So having a series of these piezoelectric elements can do all kind of sensing, ultrasound generation, and provide energy for wireless and for ultrasound. So people are working on such applications. So it's not generation of a large amounts of electrical power, rather very small parts where it is inconvenient to have batteries, where batteries may not work, for example, because temperatures are high and so on. People also want to use piezoelectric elements for pressure monitoring inside tires. There are other applications. You can use piezoelectric sensors also in a human body. This hasn't been done yet, but people are thinking about that. For example, if you have artificial hips and you want to monitor whether there is a crack developing, either in a part that is implanted or in a bones around it, well, it would be nice again to have some system of piezoelectric pressure sensors, which could also send wireless signals and so on. For this, you would need non-toxic piezoelectric materials. So either if you use lead-based, they would have to be encapsulated, or preferably you would use something that doesn't contain lead. So I will finish this part by comparing quartz versus ferroelectric piezoelectric sensors. And when I say quartz, I mean also other crystals which are comparable to quartz, like langasites, gallium phosphate, and so on. Quartz has excellent resistivity, stability, chemical and mechanical, good mechanical properties, but very low sensitivity. So it requires more expensive electronics. Ferroelectric materials, on the other hand, have much higher sensitivity, but in general exhibit hysteresis, aging, char drifts due to conductivity and pyroelectric effect, dipoling, dependent nonlinearity, and these effects are especially strong at high temperatures, low frequencies, large AC field where you have hysteresis, and so on. And at low dynamic pressures, there would be interference with pyroelectric effect and charge drifts. This doesn't, I'm not saying for the moment that ferroelectric sensors are not good. They are excellent, and they are used probably more than quartz for sensors. I'm just saying that you should have this in mind, and then use quartz for some applications and ferroelectrics for other applications. You should be aware of these possible issues. We can make ferroelectric materials, as I have shown you, with a D33 10 times bigger than in quartz, which are almost as stable as quartz, or even with a better stability, they can go to higher temperatures. There are such ferroelectric materials, for example, some of these bismuth titanate compositions that I have showed before, and you get higher sensitivity, 10 times bigger than quartz. This would be the end of my presentation on sensors. We will mention sensor applications also when we discuss transducers, ultrasound transducers.